Okay, imagine you've got this super smart machine, right? And it's learned really well how to sort fruit. Red, round, apple. Yellow, curved. Banana, easy.
Sounds simple enough.
But then, picture the same machine suddenly seeing, I don't know, a squirrel darting past.
Mm,
Furry, fast. Definitely not a fruit.
right. Completely different category.
Exactly. And that little kind of funny scenario, it actually gets us right into a really important topic. What happens when the rules a machine learns just, well, don't work for something totally new? It's this problem called data mismatch.
It is. And, what's really interesting is how we react. When these systems hit data they weren't built for, our first thought might be, okay, let's just force it to understand.
Yeah, make it learn the squirrel somehow.
Kind of. But as the sources we're looking at today show, trying to force that fit, it can often lead you down completely the wrong path. We're going to dive into why it's so tough for machines to spot patterns when the new information is just fundamentally different.
Okay, so our mission for this deep dive is basically to get a handle on the smartest way to deal with this unexpected stuff.
Hmm.
It's about like understanding the power of knowing your limits, especially for these AI brains.
Recognizing limitations.
We've got some great examples lined up sticking with our fruits, but bringing in animals now just to make these ideas, which can get a bit technical, really clear for you.
Sounds good.
All right, let's unpack this then. Data mismatch. What actually is it in simple terms?
Well, think back to that fruit sorter. Data mismatch is basically the gap, the difference between the data the machine learned from all those apples and bananas and the new data it suddenly encounters, like our squirrel.
Okay, a gap.
And when that gap is really wide, the patterns the machine learned so carefully, like red and round means apple, they just don't fit the new thing. They don't apply.
Right. So the machine has this solid rule, red, round, sweet apple, nailed it. But then, bam, gets hit with red wings, lives in foresty bird.
Totally different characteristics. Different world almost.
Yeah, not just different values, but different kinds of features altogether.
Precisely. And our sources make this point. A system trained only on fruit, when it sees an animal, might try its best to sort of force it into what it knows. It might see that red patch on the bird.
Or maybe the squirrel's general shape.
Exactly. And it might genuinely wonder, is this some weird kind of apple? Because its whole understanding, its entire frame of reference, is built around fruit. The core issue is that fundamental difference. Fruit versus animal. That's the mismatch.
Okay, so it's struggling because it's applying fruit logic in a non-fruit world. That makes sense. But what's the deep reason? Why can't it just, figure it out, adjust?
That really gets to the core of how these machines work pattern matching. They learned by finding these recurring rules, these relationships, in the data they were trained on.
So if its whole life has been fruits.
Then it gets really good at rules like red often means apple.
Yeah.
But the limitation pops up when the new data just plays by a completely different set of rules. Different characteristics matter.
Got it. So red means apple works great in the fruit bowl. But out in the woods, red might mean a cardinal or a berry or something else entirely. The machine's past just didn't prepare it.
That's it, exactly. And the sources really highlight the consequence, incorrect conclusions. The fruit machine sees the red bird and confidently shouts, apple!
Even though it's completely wrong.
Right. Its pattern finding skill is powerful within its training zone, but it just falls apart when it steps outside.
Okay, crystal clear on what data mismatch is and why it happens, these limits of pattern matching. Now, this is where it gets super interesting. What do we do about it? The sources talk about two main ways of thinking. Let's start with the first one, the problem-solving approach. What's that about?
So this approach is very direct. It sees the mismatch, sees the errors, and says, right, we need to fix this problem at the root. The goal is to eliminate the mismatch itself.
How, what does that look like in practice?
Often, it means retraining the system. You'd feed it the new kind of data, the animal data, in our example, hoping it learns to handle both. Or you might try to tweak the data somehow to make it fit better.
Okay, so with our fruit expert machine, you'd try to make it an animal expert too by, well, what would you do?
You do exactly that. You start feeding it animal data, mix it in with the fruit data. The idea, the hope, is to broaden its horizons, its knowledge base.
I can see why that sounds like a good idea initially, make it smarter, more capable. But what actually happens when you try and squish these totally different things together, fruits and animals?
Well, this is where the sources point out the pitfalls. You often end up with, frankly, illogical results. Nonsense sometimes.
How so?
If you force animal data into a system built purely on fruit logic, the machine might start looking for fruit features in the animals. It gets confused. The text actually uses the example, red bird, apple.
Huh. It's trying to connect dots that just aren't there in the original picture.
Exactly. It's trying to apply its fruit rules where they just don't belong. Now, that might sound a bit silly with fruits and animals, but imagine this in a medical context.
Oh, right. Like a system trained on symptom X, always meaning disease Y.
Suddenly seeing symptom Z, which looks a bit like X, and concluding it must be disease Y, even if Z actually points to something totally different and requires different treatment.
Yeah, that could be really dangerous. That really drives home the importance of getting this right.
It does. The consequences of mismatch aren't just academic.
So, what are the big downsides then, the limitations of trying to force this problem-solving fix when the data types are just fundamentally poles apart?
The main ones highlighted are, first, you actually risk increasing errors. The machine gets confused, maybe even messes up the fruit classifications it used to get right.
So it gets worse, not better.
Potentially, yeah. And second, it's often a huge waste of time, effort, and computing resources. You're trying to achieve something that might be fundamentally impossible or at least incredibly inefficient with that particular model structure.
It's like, I don't know, trying to teach a fish to climb a tree by showing it lots of squirrels. It's just not built for it.
That's a pretty good analogy, actually. The source material suggests this force approach often leads to systems that are confused and less reliable overall.
Okay, so forcing a solution can backfire badly, which brings us neatly to the second way of thinking our sources talk about. This one sounds, well, more realistic, maybe. Problem mitigation. What's the philosophy there?
It's a totally different mindset, really. Instead of trying to eliminate the mismatch, it starts by acknowledging it. It accepts that maybe, just maybe, a perfect unified solution isn't possible or practical, especially with really different data.
So it doesn't try to fix the root cause, but manages the fallout.
Exactly. The focus shifts entirely to minimizing the bad outcomes, the wrong answers, the potential harm, the wasted effort.
Okay, so back to our fruit machine and the squirrel. If it's using mitigation, what does it do when the squirrel shows up? It doesn't try to classify it as a weird apple. So what does it do?
The analogy used in the source is really helpful here. The machine basically recognizes, hang on, this data. It's not what I know. I can't process this properly.
Yeah.
And then it stops.
It just stops.
It stops trying to classify it within its existing fruit framework, yes. It flags it as something outside its expertise.
So the machine sees the squirrel and effectively says, nope, not a fruit, cannot compute using my fruit rules.
That's pretty much it. The example given is direct. The system encounters animal data and declares, this is not fruit. I can't process it. It admits its limits instead of guessing wrong.
That sounds incredibly sensible, actually, much safer. What are the advantages listed for doing it this way? Why is saying, I don't know, often better?
The benefits are pretty significant. First, like you said, safety. No errors. By refusing to classify something it doesn't understand, it avoids making potentially costly mistakes.
Okay, avoids errors. What else?
Second, it saves time and resources. No computation wasted trying to force that square peg into a round hole.
Makes sense. Efficiency.
And third, maybe a bit counterintuitively, it can actually build more trust with the user.
How so? By admitting it doesn't know.
Yeah. When a system is upfront about its limitations, I'm great at fruits, but I don't do animals, users learn to trust its judgments within its competence zone. They know when its answers are reliable.
Right. Better to get no answer than a wrong answer you might mistakenly trust. Okay, that clicks. Now, our sources seem to lean towards this mitigation approach being often the better strategy. Why is that the core argument?
It really comes back to those fundamental differences in the data we talked about. The sources, especially the second one, link this strongly to the limits of inductive reasoning.
Inductive reasoning, remind me.
That's how we and machines build general rules from specific examples. You see lots of apples, you induce the rule, round red things are often apples.
Got it. Learning from experience.
Right, but data mismatch shows the edges of that. If your only experience is fruit, your induced rules are only about fruit. They simply don't work, they're invalid. When you suddenly see an animal, the game changes.
And the problem-solving approach kind of ignores that limitation.
Exactly. It tries to stretch those fruit-based rules to cover animals, which inductive reasoning says you can't reliably do. Mitigation, on the other hand, respects those limits. It recognizes the rules don't apply here.
You can't just keep showing the machine more apples and hope it magically understands fur.
Precisely. So mitigation wins on safety, Avoiding bad answers is key, especially in high-stakes areas.
Hmm.
It's often simpler, stopping is less complex than a messy, forced integration.
Less engineering effort, too, probably.
Definitely. And there's that honesty or transparency aspect, saying, I can't do that, builds user understanding and realistic expectations. The source puts it bluntly. Fruit machine sees animal, says, not fruit, processing impossible, and stops. Clean.
Okay, sold on mitigation being smart in these cases. What are some actual practical ways the sources suggest we can do mitigation? How does it look on the ground?
They list a few concrete techniques. One is trying to screen the data before it hits the main classification engine, like check first. Does this have fur, wings? Okay, probably an animal, don't send it to the fruit classifier.
Pre-filtering, basically.
Exactly. Another is just that hard stop. When the main engine gets data that looks weird or gives low confidence scores, it just halts and flags it.
Oh.
Cannot process this. Like stating explicitly, animal data detected, cannot classify as fruit.
A clear rejection.
Right. And a third way is to capture that rejected data. Don't just throw it away. Store it separately
What?
for later analysis.
Hmm.
Maybe you collect enough animal examples that you realize you need a separate animal identification system. It informs future development without messing up your current working fruit system.
So identify upfront if possible, stop if unsure, and maybe learn from the rejects later in a different context.
Smart. Now, you mentioned the second source links this heavily to inductive reasoning limitations. Can we elaborate on that connection a bit more? Yeah, it's a key point. Data mismatch is basically a real-world manifestation of the limits of induction. You form general rules, all swans are white, based on your limited data, seeing only white swans. Then you encounter radically different data, a black swan in Australia, and your rule breaks.
The mismatch.
Right. Trying to force a solution, like saying the black swan must be a weird type of white swan, ignores the fact that your initial data was too narrow to form a universal rule. It leads to flawed conclusions. The source is a bear is a fruit kind of error. Mitigation accepts the limit. My swan rule was based on European data. This new data requires a revised rule or maybe a different framework.
It's like me trying to understand, say, all global politics based only on news from my hometown. My induced rules would be way off when faced with international events.
Perfect analogy. And this has really big implications when we think about today's really powerful AI, like large language models, LLMs. How does data mismatch play out there?
Yeah, this is fascinating because LLMs are pattern matching wizards with text, right? But the source suggests they might have this tendency to always try and give an answer, even if the input is totally mismatched from their training.
That's the concern raised, yes. Because they're trained on such vast amounts of primarily text data and are designed to generate coherent linguistic output, they often default to finding some connection, generating some response.
Even if it doesn't really make sense.
Potentially. The danger is they might not have a built-in robust mechanism to recognize, whoa, this question or prompt is about something completely outside my knowledge base derived from text, finance, code, etc.
Yeah.
Instead of saying, I don't know, or that's outside my scope, they might try to construct an answer that sounds plausible.
But is actually wrong or based on faulty assumptions because of the mismatch. Like our fruit machine trying to describe fur using fruit skin terms.
Or, the example the source uses is maybe more subtle, but equally problematic for LLMs. Faced with a task involving fundamentally different data, like, say, analyzing complex scientific experimental results formatted weirdly, the LLM might suggest a solution like, just retrain me on data like this.
Which sounds helpful, like the problem-solving approach.
Right, but it might be the wrong solution. If the LLM's core architecture is optimized for language patterns, simply dumping in radically different structured data might not work well, could confuse its existing abilities, and might be vastly less efficient than, say, using a specialized tool or model for that data type.
So the LLM, trying to be helpful, might actually recommend an ineffective brute force solution because it doesn't recognize the fundamental mismatch and the need for a different kind of tool.
That's the potential issue highlighted.
Yeah.
It really underscores why even these advanced models need better mechanisms for the mitigation approach, the ability to recognize their limits and say, this isn't my area or this requires a different approach, rather than always trying to force an answer within their existing framework.
That makes a lot of sense. Our second source even helpfully includes a table comparing the two approaches side by side. We don't need to read it out, but maybe hit the key contrasts again.
Sure. So, big picture. Problem solving aims to eliminate the mismatch, assumes a solution is usually possible, often uses retraining. Outcome in the fruit-animal case. Maybe a wrong answer like red bird, it's apple.
Right. And mitigation.
Mitigation aims to minimize negative outcomes from the mismatch. accepts limitations, often linked to inductive reasoning, uses methods like detection and stopping. Outcome, not fruit, cannot process.
Advantages of mitigation in these cases being?
Avoiding errors, saving resources, building trust. The downside is it doesn't solve the underlying need to process the new data type. It just manages the immediate problem.
And the implication for LLMs?
They often default to problem solving, but really need to get better at mitigation for handling fundamentally different inputs reliably and safely.
Perfect summary. That table sounds like a really useful way to see it laid out. So wrapping this up, the big aha moment from our deep dive today really feels like this. When you're dealing with information or situations that are just fundamentally different from what your system or even you knows, trying to force it to fit the old mold isn't always the smartest play.
No, definitely not.
Sometimes the most intelligent, the most effective response is actually to recognize the limits, to acknowledge my current rules don't apply here, and avoid making a bad call based on faulty assumptions. It's that realization that saying, I can't process this right now, can be the right answer.
It absolutely can. And, this isn't just about machines. It echoes through so many other things, doesn't it? How we approach problems or unfamiliar situations in our own lives.
Right.
Totally. Which leads me to a final thought for you, listening in. Where in your own life, maybe at work, maybe personally, might you be pushing too hard to make something fit your existing framework, when perhaps stepping back and acknowledging, okay, this is different, my usual approach might not work here, could actually lead to a better, safer, or more efficient outcome?
It's a great question to ponder. That need to recognize limits and handle mismatches smartly, it crops up everywhere once you start looking for it.
Definitely food for thought. It's a principle that seems to apply way beyond just sorting fruits and animals. Thanks for unpacking all that with me today.
A pleasure. Really interesting stuff.